Today, we're going to be covering Chapter 2 on probability distributions. This includes discrete distributions, continuous distributions, Poisson process, and Monte Carlo simulation. In this video, we'll be focusing on two topics, discrete and continuous distributions. And in next week's video, I'll be discussing Poisson process and Monte Carlo simulation. For those of you preparing for the CS1 exam, this video is for you. Probability distribution. A probability distribution simply tells us how probabilities are assigned to possible values of a random variable. Instead of listing things randomly, it gives us a clear and structured way to see how likely different outcomes are. Distributions are of two types, discrete and continuous. I can't emphasize enough on how important these are. A discrete distribution is used when the random variable takes specific countable values. For example, the number of heads in 3 coin tosses can only be either 0, 1, 2, or 3. A continuous distribution, on the other hand, is used when the variable can take any value within a range. For example, the heights of students in this range can be either 170.2 centimeters or 185.6 centimeters, etc. For discrete random variables, to calculate the probability of an event, we use something called a probability mass function, written as probability of random variable x given small x. This gives us the probability of each value, and all probabilities must add up to 1. For continuous random variables, to calculate the probability of an event, we use probability density function denoted by the function of x. Here, we do not find probability at a single point. Instead, we find probability over an interval using integration. The total area under the curve is equal to 1. Before we begin discussing each type of distribution individually, let's talk about tables. In your exam, a book with tables is allowed. For the IFoA, this book is called Formulae and Tables for Examinations, and other actuarial bodies also have their own versions. It contains all important formulas and probability tables for this chapter as well as for other chapters. Most of the formulas you need are already given there, so the focus is not on memorizing but on understanding how to apply the concepts correctly. We are now beginning with discrete distributions. These are broadly of 8 types, and the first one we study is Bernoulli distribution. A Bernoulli distribution represents a single trial with either of the two outcomes, success or failure. For example, the probability of a biased coin landing on heads is 0.6. Calculate the probability for success, failure. The parameters are P is the probability of success, and Q, which is 1 minus P, is the probability of failure. The probability mass function is equal to the probability of success upon the random variable into the probability of failure upon 1 minus the random variable. The mean is P, that is the probability of success, and the variance is P into Q. Let's derive this. We will derive the expectation and the variance only for Bernoulli distribution to understand the method. For other distributions, we will use the results directly. As covered earlier, X can have only two outcomes, either success or failure. We denote the random variable x is equal to 1 for success and x is equal to 0 for failure. The probability of x is equal to 1, that is, the probability of success is equal to p, and the probability of x is equal to 0, that is, the probability of failure is equal to q. To calculate the mean, we use the following formula. The expectation of x is equal to the summation of the random variable x times the probability of x. When x is equal to 0, the probability of x is equal to q, plus when x is 1, the probability of x is p. This gives us the expectation as p. The variance of x is equal to expectation of x square minus expectation of x whole square. The expectation of x square is equal to Now, the variance of x will be expectation of x square, which is p, minus expectation of x whole square, which is p whole square. Using these formulas and this method, we can derive the mean and the variance for other distributions as well. The standard deviation is simply the square root of the variance. Now, solving the example, the parameters are p, which is the probability of success, equal to 0.6, and q, which is the probability of failure, is 0.4. The probability of success is 0.6 to the power 1 into 0.4 to the power 1 minus 1. This gives us 0.6. The probability of failure is equal to 0.6 to the power 0 into 0.4 to the power 1, which gives us 0.4. Binomial distribution. A binomial distribution represents the number of successes in a fixed number of trials. For example, a fair coin is tossed 4 times. Find the probability of exactly 2 heads. Here we are given a fixed number of trials equal to 4, since the fair coin has to be tossed 4 times, and the number of successes is 2, since we have to find the probability of getting exactly 2 heads. Since we are to find 2 successes in 4 fixed trials, this question follows the binomial distribution. The parameters are n is the number of trials, p is the probability of success, q is the probability of failure. To find the probability mass function, we take the number of combinations of choosing x successes out of n trials multiplied by the probability of success raised to the number of successes multiplied by the probability of failure raised to the remaining trials. The mean is n multiplied by p and the variance is n multiplied by p multiplied by q. Now, getting to the question, n is 4, p is 0.5 and x is 2. P is 0.5 since a fair coin is tossed, which gives an equal probability of heads or tails. Uniform distribution. A discrete uniform distribution is a distribution where all values of a random variable are equally likely. So, there is no value that is more likely than the other. Everything has the same probability. For example, a dice is rolled. Find the probability of getting 2. We use A, which is the smallest value, B, which is the largest value, and H, which is the common difference. So the values follow a pattern like A plus H, A plus 2H, all the way to B. The mean is A plus B upon 2, and the variance is B minus A into B minus A plus 2H divided by 12. Now, solving the example, the outcomes we can get are 1, 2, 3, 4, 5, and 6. A is the smallest term, which is 1. B is the largest term, which is 6. And H is the common difference, which is 1. The probability is H upon B minus A plus H, which gives us 1 by 6. In this case, it's also quite easy to calculate the probability without using the formula, since all of these outcomes are equally likely when a die is thrown. However, this formula is especially useful when the random variables do not begin from 1 and don't have a gap equal to 1. For example, we have 2, 4, 6, 8, 10, and 12. Here, all of these outcomes are equally likely. Now, it would not be as easy to calculate the probability of these as it was for the die question. Probability of x equal to 2 is h divided by b minus a plus h, which would give us 1 by 6. Geometric distribution. A geometric distribution represents the number of trials required to obtain the first success. For example, a coin has the probability of success 0.4. Find the probability that the first success occurs on the third trial. The parameters are P is the probability of success and Q is 1 minus P. The probability mass function is found by taking the failure probability of all the previous trials and multiplying it by the success probability on the required trial. The mean is 1 divided by P and the variance is Q square upon P. Now, solving the question, we first identify the values of the parameters. The probability of success is given as 0.4, therefore the probability of failure will be 0.6. So we start by taking the number of failures whole upon the number of times the failure has occurred. Since the question says that the first success occurs on the third trial, it means until the third trial there was no success. So, the person has failed the first 2 times and succeeded in his third attempt. Now, let's understand an important property of the geometric distribution called the memoryless property. A distribution is said to be memoryless if the probability of future trials does not depend on what has already happened. Mathematically, we write this as probability that x is greater than x plus n given that x is greater than n is equal to the probability that x is greater than x. What this means is that if we've already waited for n trials, the probability of waiting further does not change. Now, let's derive this result step by step. We start with the conditional probability. The intersection of both of these terms is x is greater than x plus n. This is because x is greater than n means no success occurs in the first n trials. X is greater than x plus n means that no success occurs in the first x plus n trials. If no success has happened in the first x plus n trials, it automatically means that no success has happened in the first n trials as well. Because the first n trials are included inside the first x plus n trials, the event x is greater than x plus n is stronger than x is greater than n. For geometric distribution, probability that x is greater than k is equal to 1 minus p whole upon k. This is because x greater than k means that the first success has not happened in the first k trials. So all of these k trials must be failures denoted by 1 minus p. These failures would have occurred k times. So that's 1 minus p into 1 minus p into 1 minus p up to k times, written as 1 minus p to the power k. This completes the derivation. Negative binomial distribution type 1. This represents the number of trials required to obtain k successes. For example, a coin with probability 0.5 is tossed until 3 heads occur. Find the probability that this happens on the 5th trial. As mentioned earlier, this distribution represents the number of trials required to obtain k successes. Here, 5 trials are required to obtain 3 successes. Therefore, this follows negative binomial type 1. The parameters include k, which represents the number of successes, p, which is the probability of success, and q, which is 1 minus p. For the probability mass function, we take the number of combinations of arranging k minus 1 successes in the first x minus 1 trials. We multiply this with the probability of successes raised to k multiplied by the probability of failure for the remaining trials. The mean is k upon p and the variance is kq upon p square. Now let's solve the example. K is equal to 3 as according to the question we require 3 heads to be successful. P is 0.5 and Q is 0.5. X is 5. Negative binomial distribution type 2. This represents the number of failures before k successes. For example, with probability 0.5 and k equal to 3, find the probability of 2 failures. The parameters are the same as before. For the probability mass function, we take the number of combinations of arranging k successes among x plus k minus 1 trials multiplied by the probability of success raised to k multiplied the probability of failure raised to x. The mean and the variance is same as before. Solving the example, Hypergeometric distribution. This represents the number of successes when sampling without replacement. For example, a box has 5 defective and 15 good items. A sample of 4 is drawn. Find probability of exactly 1 defective item. The parameters are: capital N is the total population size, small n is the sample size, k is the number of successes, and capital N minus k is the number of failures. For the probability mass function, we take number of ways of choosing x successes from k items multiplied by the number of ways of choosing remaining items from non-success group divided by the total number of ways of choosing a sample of n items from population of n. Here you can have a look at the mean and the variance. Now solving the question is the number of successes, which over here is the defective items drawn. Since there are 5 defective items and 15 good items, k will be 5. The total population size is 5 plus 15. Small n, that is the sample size, is 4 since a sample of 4 is drawn. N minus k will be 15. X, that is the random variable, is given as 1. Poisson distribution. This represents the number of events occurring in a fixed interval at a constant rate. For example, a bakery receives an average of 3 cake orders per hour. Find the probability that it receives exactly 2 orders in a specific hour. Here, we've been given an event that is receiving 3 cake orders in a fixed interval of time, that is per hour, and the events occur independently at a constant average rate. This consists of one parameter, lambda, which denotes the average number of events. For the probability mass function, we take exponent raised to the power minus lambda multiplied by lambda to the power x whole upon x factorial. The mean and variance is lambda. Now, solving the question, lambda is the average number of events which is given as 3. X, which is the random variable, is 2. Now we begin with continuous distributions. The first one is uniform distribution, but the continuous case. This exists for continuous random variables between a and b, that is, in a given range, such that all values in this range are equally likely. For example, the wait time for a bus is uniformly distributed between 0 to 15 minutes. Find the probability density function. The parameters include a, which is the lower limit, and b, which is the upper limit. The probability density function for this is 1 upon b minus a. The mean is a plus b upon 2, and the variance is b minus a whole square upon 12. Now, let's look at how the mean and the variance is derived for continuous distributions. We will derive these for the uniform continuous distribution to understand the method. For other distributions, we will use the results directly. The expectation or the mean is equal to x times the probability of x. Since continuous distributions cover a range, instead of using the summation sign, we will be using integrals. Similarly, the variance of x will be expectation of x square minus expectation of x whole square. Now, solving the example. Gamma distribution. This models the waiting time until a certain alpha number of events occur, with events happening at a constant rate. To understand this, it's important to understand the gamma function. It's easy to calculate factorial for whole numbers. However, factorials don't work for non-integers like decimals and fractions. Therefore, we want a function that works as a factorial but for such types of numbers. The gamma function is defined as follows and is basically a continuous version of a factorial. This integral is designed in such a way to grow like a factorial but also to decay fast enough so that the total area stays finite. In distributions like gamma distribution, we need a constant to make the total probability equal to 1. The original gamma function is not a PDF since the total area is not equal to 1. Therefore, we multiply it by a constant and then solve the integral. We use substitution to find the value of C and then input it in the PDF. The examples for this will be covered under the chi-square method. The parameters include alpha, which is the shape parameter, and lambda, which is the rate parameter. The mean is alpha upon lambda and the variance is alpha upon lambda square. The gamma distribution has two special cases: exponential distribution and chi-square distribution. We start with exponential distribution. This distribution models the wait time until the first event occurs, where every event occurs continuously and at a constant rate. Here, alpha is equal to 1. For example, flash floods occur at a constant average rate. The time between the floods follows an exponential distribution with a mean of 20 years. Find the likelihood of a flash flood exactly 30 years after the previous. The parameters include lambda, which is the rate parameter. The probability density function is lambda into exponent to the power minus lambda x. The expectation is 1 upon lambda and the variance is 1 upon lambda square. Now, to solve the question, it's important to identify the parameter lambda. Since the exponential distribution has a mean of 20 years and we know that the mean is equal to 1 upon lambda, therefore we have 20 is equal to 1 upon lambda, which makes lambda equal to 1 upon 20. The probability that the flood occurs exactly 30 years after the previous one is given by The second subtype we'll be covering is chi-square distribution. This is a special case with alpha equal to v upon 2, where v represents the degrees of freedom, and lambda equal to 1 by 2. For example, x follows gamma 2, 1.5. Calculate probability that x is greater than 4. As discussed earlier, V stands for degrees of freedom. The probability density function is listed here. The expectation is the degrees of freedom, and the variance is 2 times the degrees of freedom. Its relationship with the gamma distribution is crucial since it makes it much easier to solve gamma distribution based questions. Solving this question, which is based on the gamma distribution, we have alpha is equal to 2 and lambda, which is equal to 1.5. However, under the chi-square distribution, alpha is always supposed to be v upon 2 and lambda is supposed to be 1 upon 2. So we can write alpha as 4 upon 2, where v, or the degrees of freedom, becomes 4. However, we can't write 1.5 as 1 by 2. Lambda is 3 by 2, which is 3 times of 1 by 2. So, to calculate probability of x is greater than 4, we multiply this function by 3. Then, we substitute the 3x. Let's understand how this happened. After we multiplied the probability function by 3, which is essential since there is an additional 3 here, we proceed to taking in account this relationship which we had studied earlier. Here we have 2 lambda x, which is 2 times 3 by 2 times x, which gives us 3x. According to this relationship, this follows chi-square with degrees of freedom 2 alpha. This will tend to chi-square 2 times 2, which is 4. Now, we are supposed to refer to the table book to find this value. So we look for the variable which has degrees of freedom 4 and corresponds to the random variable 4. This gives us 1 minus 0.9826. We subtract this from 1 since chi-square distribution, like most other distributions, give left tail probabilities. So for greater than, we use the complement. Beta distribution. This is defined on the interval 0 to 1. And it models random variables representing proportions or probabilities. To understand this, let's start by understanding the beta function. We often see integrals in this form. These are very common but also not very easy to solve. Therefore, we define a function to represent this entire integral in one term, known as the beta function. Its connection with the gamma function should also be noted. Now, let's understand the derivation of the PDF. We want a function which is greater than equal to 0 and which gives the total area equal to 1. The function which already exists is not a PDF since the area is not equal to 1. Therefore, we multiply it by a constant the same way we did for the gamma distribution. Then we recognize this integral as the beta function and input it to find the value of c. Hence, we derive our PDF. The parameters include alpha, which is the shape parameter, and beta, which is also the shape parameter. Also, take into account the mean and the variance. For CS1, the beta distribution is asked less frequently compared to other continuous distributions. Normal distribution. The normal distribution is a continuous distribution about the mean and forms a bell-shaped curve. For example, if x tends to normal 25, 36, calculate probability that x is less than 28. The parameters include mu, which is the mean, and sigma square, which is the variance. This is the probability density function. The mean is represented by mu and the variance is represented by sigma square. For normal distribution, we have been provided with a standard normal variable. This is it has mean equal to 0 and standard deviation equal to 1. We're supposed to find the probability that x is less than 28. So we start by converting x into the standard normal variable z. So we write this as z is less than x minus mu upon standard deviation. As we can see here under the notation, the two values written in the bracket next to n give the mean and the variance respectively. From that, we know that the mean is 25 and the standard deviation is root 36. We now solve this to obtain 0.5. Now, we use the table book to find the value where z is 0.5. This gives us 0.69146. Lognormal distribution. A variable follows a lognormal distribution if its logarithm is normally distributed. For example, if w tends to lognormal 5,6, calculate the probability that w is greater than 3000. The parameters are the same as the normal distribution. Here we have the probability density function, the mean, and the variance. Note that compared to the normal distribution, there is an additional x here, and this x becomes logarithmic x. The mean and the variance also vary. Now, let's look at the example. If w tends to lognormal 5,6, then log w will tend to normal 5,6. We're always supposed to convert it to this form when we solve a question. To find the probability that w is greater than 3000, we do the same thing here that we did here. If w is greater than 3000, this means that log w is greater than log 3000, which gives us 8.006. Now we replace log w by z as we did for normal distribution and follow the same steps. T-distribution. This looks similar to a normal distribution, but the tails are heavier. It's mainly used when the sample size is small and the population variance is unknown. For example, x tends to t with the degrees of freedom 5. Find the probability that x is greater than 2.015. The PDF for this is z upon under root x upon v, where z is the standard normal variable. It's also important to note that the t-distribution table gives upper tail or right tail probabilities. This gives us the answer as 0.05. F distribution. The formal definition states that if the random variable x follows chi-square distribution with the degrees of freedom m, and the random variable y follows chi-square distribution with the degrees of freedom n, such that both of these random variables are independent, then f will be equal to x upon m whole upon y upon n, with parameters m and n respectively. For example, let f follow f of 4, 6. Find the probability that f is greater than 4.53. The parameters include v, which represents the degrees of freedom. The probability density function is the same as we discussed above, which is the value of f. Some important points are: tables for the f distribution, like that for the t distribution, give upper tail probabilities. The second important probability is that the reciprocal of f with the parameters m and n follows f with the parameters n and m, that is, the order is reversed. The main objective for this is to compare two variances. Before this, let's understand how to use the f tables. F tables are arranged by significance levels like 10%, 5%, 1%, etc. Each table gives a critical value f such that probability that f is greater than f is equal to the significance level. Inside the table, the numerator of the degrees of freedom, or m, are across the top, and the denominator degrees of freedom are down the side. So the process includes choosing a table based on the significance level, locating m and n, and reading the value of f. The value that corresponds becomes the significance level. So, directly, the probability that f is greater than 4.53 becomes 0.05. Now that we've covered all distributions, let's briefly understand CDF. CDF stands for Cumulative Distribution Function. It's represented by function of x, where the f is capital. It simply gives us the probability that the random variable x is less than or equal to a certain number. They can be found by integrating the PDF. Let's discuss these for a few distributions because these are the ones where CDF can be easily calculated in a closed form. For others, like normal or chi-square distribution, we rely on tables instead. For the uniform distribution, the CDF is x minus a upon b minus a. This is obtained by integrating the PDF from a to x. For the exponential distribution, the CDF is given by 1 minus exponent to the power minus lambda x. This is obtained by integrating the PDF from 0 to x. The reason why we integrated from a here is because the value of x begins from a, whereas here the value of x begins from 0. That's why we integrate from 0 all the way to x. This brings us to the end of today's video. I'll be back next week on Actuarial Simplified with part 2 of this chapter covering Poisson process and Monte Carlo simulation. See you in the next one.